Today our topic is layer structure interaction analysis. So main issue for this layer structure interaction, it came from the continuously weighted layer. In order to reduce the impact force when there is any connection between the layers. Also, in order to increase the life cycle of the layer and for better smooth learning, we prefer to have the continuous weighted layer, which may have longer than 200 meters. And when we use this continuously weighted layer, as its length is very long, so we need to be very careful about the deformation, also the axial stress. For example, when the temperature raises, there could be the buckling in the layer. Also, when there is the temperature drop, we need to be careful about the fracture failure. If we see more detail about this interaction, so this is the layer at the top, and this is the deck. So between the layer and deck, there will be the ballast. So when the train is there, and traction load or braking force can be applied to the layer, this longitudinal force, some of them can go to the connected piers or abutment, and some of the traction and braking load will be transferred to the embankment part, which means this longitudinal load will move along with the layer and then it will be conveyed to the embankment. Because of this action, we will have a certain axial force, axial stress on the layer. Also, if there is the extension in the layer due to the train vertical load and temperature load, as you can see from these pictures, continuous layer will restrain the free movement of the deck due to the ballast. And because of this restraint, deck deformation will acquire certain axial force, both in the layer and the deck. This is the axial force on the deck and the layer. First picture is the axial force of the layer in the embankment part. And this is the axial force of the layer on the bridge part. So if for the embankment part, if the layer and embankment is rigidly connected, then its axial force will have the certain value like F, which came from the temperature variation. But since the rigid force, the restraint condition is not the rigid between the layer and embankment, so there must be the certain deformation in the layer. Because of this deformation, the axial force will be decreased. So you can see those decreased axial force on each end of the layer for the embankment part. In case of the deck part, if for the layer forces, if there is any thermal load, due to the temperature increase and decrease, the deck will be deformed. In this case, the layer deformation will be restrained by the shear resistance of the ballast. Therefore, the maximum deformation will occur at the center of the deck, as you can see from this picture, and the maximum and minimum axial force will occur at the end of the deck. So each standard, like the UIC or Eurocode or the American standard, each of the standards provide certain design requirements for the rail stress and the relative displacement between the rail and deck, and also the displacement due to the rotation of the deck. And you can see the certain criteria from here. So in order to satisfy this condition, we need to have the model which can consider the rail structure interaction. What type of the load do we need to consider for this rail structure interaction? Firstly, we need to consider the thermal load. Thermal load can be applied for both rail and deck. Generally, we only apply the thermal load to the rail, but if there is any extension joint, then we need to consider this thermal load for both rail and deck. So for the summer and winter, we can apply certain thermal load based on the specification. Similarly, we need to consider the traction and braking load due to the train. And finally, we need to consider the train vertical load. So from this train vertical load, we will check the stability on the gravel ballast due to the rotation of the deck. After having this separate loading effect, then we need to check its combined effect. How to check it? One thing we need to be careful is when there is the train load and with and without train load, the ballast stiffness will be different. So in this case, as the spring stiffness is changed, generally we cannot do such a linear summation for the thermal load and train loads. However, as the code specified, we can do the linear summation, so we can do such the loading combination effect, just simply summating the results for each of the loading effect. After we check the axial stress and deformation, then if our stress or deformation is not satisfied, then we need to redesign it. In this case, we will try to change some of the condition, like the support layout and span composition, stiffness of the deck. Also, we will review the zero longitudinal resistance rail fastener, which is just like this picture. So this GLR has the no restraint in the longitudinal direction, so rail can be moved freely in the longitudinal direction, but it will restrain only the transverse and the vertical direction. So by installing this GLR, we can reduce the maximum stress. If the zero longitudinal resistance fastener is not satisfied, finally we will review the expansion joint. But as I mentioned at the beginning, expansion joint is not really recommended because of the maintenance fee and the impact force. So this is the procedure that I just explained.